You guys have any midterm test or what? Do you have a midterm test? Okay. 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 Good morning, everybody on the Zoom. All right. About quiz 5, I think is easy. Well, compared to quiz 4, is similar. So I think most of you have done better in quiz 5 than in quiz 4 in general. So I will have them marked this afternoon, and I will try to return them to you later today. Okay. Right. So last week we talked about value at risk and expected shortfall, the two financial risk measures. Hello, guys.
Hello.
Yeah, and we talked about some of their properties, the proofs of the properties, and the simplified expressions for the two measures, VAR and ES, right? Now, and I also did quite a few examples on deriving expressions for the two risk measures, VAR and ES, right? Okay, now it's good having the expressions, it's good deriving the expressions for VAR and ES, but unless you can estimate them, it's not of practical use. I mean, in order to use the formulas for VAR and expected shortfall, you need to be able to estimate those formulas. So that's what I'm going to start talking about today. So there are three kinds of estimations for VAR: the parametric estimation, non-parametric estimation, and semi-parametric estimation. I hope you guys looked at the videos. There were 3 videos I asked you guys to have a look, right? All right, so before I go to the videos, this is a recap on what you probably did in second year in statistical methods. I mean, if you haven't taken that course, I mean, you may still be familiar with this material. But if you're not familiar with this material, please make sure you are, because I put all the videos. I used to teach that course a long time ago, the course called Stat Methods. And I put the videos from my teaching on a YouTube channel. I think I sent you the link for the YouTube channel. So if you haven't done that course, or if you don't remember anything from the course, just have a look at the YouTube channel. Okay. So it's basically things like this. Like if you have an estimated theta hat of theta, then it's unbiased if bias, which is defined as this, is equal to 0. And is asymptotically unbiased if the limit of the bias is 0, right? And it's consistent if the limit of the MSC is a mean squared error defined by this. So if the limit of the MSC is 0, then the estimator is said to be consistent. So this is a website. This is a website containing my material for statistical methods, but there's also a YouTube channel I created. I think I sent you guys a link. If you can't find the link, just email me. I will send it back to you, right? Okay. Anyway, you need to know all this stuff because you will get questions on bias and MSC and all kind of stuff like that in the exam. So if you don't remember, or if you haven't done this, please make sure you learn this material. Okay. All right. All right. So there's 3 kind of estimation methods: the parametric estimation method, which is what I'm going to focus now, Now suppose the losses are IID with normal parameters mu and sigma squared. And then we know from last week that the formula for var is given by this. And you should know from statistical methods that the estimator for mu is the sample mean, the estimator for sigma is given by this. And hence the estimator for var is given by this. It can be shown that this estimator is asymptotically unbiased and consistent. I'll come back to that later. Okay. So that's the first of the parametric methods, right? The second of the parametric methods assumes that the losses are uniformly distributed from A to B. So this is the formula for var, which we did last week. We derived this last week. And again, from stat methods, you should know that the estimators for A and B are the min and the maximum, or the smallest and the largest data points. So hence the MLE for var, I should say there's a big var. MLE for var is A hat plus P times B hat minus A. Okay. All right, and it can be shown that this is asymptotically unbiased and consistent. Right. Now the third parametric estimation method is I'm assuming that the losses are exponentially distributed with parameter lambda. In this case, we showed last week that the formula for var is given by this. And you should know from stat methods that the MLE for lambda hat is this. And hence the MLE for var is this. And it can be shown that this is unbiased and consistent. That's the third parametric method. Guys, if you have any questions, those of you on Zoom, please use the chat room as usual, right? And the fourth parametric method is assuming that the losses are IID from this CDF. And for this, the var is given by this. I think I showed this last week. Maybe not, I don't know. I think I did this last week, yeah. And it can be shown by the method of maximum likelihood that the estimator for A, the only parameter, is given by this. Yeah. And the second derivative is negative. So this is indeed an MLE for A, right? And hence the MLE for var, the MLE for var is given by P to the power 1 over A hat, which is this. Yeah. Okay. So that's the fourth of the parametric methods. The fifth of the parametric method is known as the variance covariance method. In this case, you have a portfolio with M independent investments. And suppose Xi denotes the loss on investment I and Wi denotes the weight on investment I. Because some investments may be more important than others. So you have weights there are M investments, right? Now, if we assume that Xi are normally distributed, right, II independent, then you should know from stat methods that the distribution of X will be this, with this being the mean and this being the variance. Yeah, do you know this? Do you remember this result from? You must have done this ages ago. Yeah. Come on. If you don't remember, just look back on the stuff you guys did last year or the year before. I think I did cover this in Intro to Stats also. I'm not sure. I think so. Yeah. Anyway, so all right. So using the fact that X has this normal distribution, you can work out the var. You can show that the var is given by this formula, right? Okay. And in order to estimate this formula, you need to estimate the mu i's and the sigma I squared. Mu I is the mean of the xi, which is the loss on investment I, and sigma I squared is the variance of xi, which is the loss on investment I. Right, now suppose you have the following data. I'm going slowly in case just suppose you have the following data. Suppose you have this data on X1, which is the loss on the first investment. Suppose you have this data on X2, the loss on the second investment. Suppose you have this data on XM, which is the loss on the mth investment. Right, then you should know from stat methods that this is the estimate for mu hat I, right? And this is the estimate for sigma I squared, right? Okay. So hence the estimate, the MLE for VAR is given by this formula here. Okay. Any questions so far, guys? Anyone in Zoom want to ask questions, please feel free. You guys okay? All right, so that's the fifth of parametric method. The sixth and the final parametric method is based on Weibull distribution. Weibull is a Swedish engineer who invented this distribution. I think he worked for the Swedish car company. I can't remember the car, the brand of the car. I used to remember it. Anyway, so this is the CDF of the Weibull. Now setting this equal to P and solving for X, this is what you get. So this is your VAR, the formula for VAR. Now there are two parameters, theta and beta. Now it can be shown that the estimator for theta hat and beta hat satisfy these two equations, where X bar is the sample mean, S squared is the sample variance, right? So hence the estimator for VAR is given by this, right? So these are the six parametric estimation methods for value at risk. Okay, the next section I'm going to talk about is non-parametric. Remember, non-parametric means that you don't assume anything about data, right? So we're assuming that we are assuming that data does not follow any particular distribution, right? Okay, the first non-parametric estimation method is known as the historical method. Historical method, right? It's easy. What you do is, suppose these are the losses. The first thing you need to do is to arrange the data. So this is the smallest of the losses, second smallest. This is the largest of the losses, right? And then the historical estimator for VAR is the ith smallest if P belongs to this interval, right? So for example, if you had this data, you arrange the data from the smallest to the largest, and suppose you want to find VAR at 0.4. So your P is 0.4, right? And 0.4 belongs to this interval, right? So it belongs to this interval. So your I is 2. And the second smallest data is 0. This is your, so the VAR is equal to 0. Right now, if P is 0.9, 0.9 belongs to this interval. So your I is 5. So the fifth smallest data point is this one, which is 5. So your VAR is equal to 5. All right, so it's very, very easy to use. The historical is perhaps the simplest of all the estimation methods for value at risk. Okay. All right. The next non-parametric estimation method is Bootstrap. Bootstrap is due to Brad Efron, who is a professor at Stanford. So the idea is it's not complicated. What you do is, suppose you have the losses x1 to xn. The first thing you do is to compute the empirical CDF, which is given by this formula here, where I denotes the, you know what the indicator function is, right? Yeah, okay. Now, if you plot this guy versus x, it will look like a ladder. So it will, if this is the smallest data, if this is the largest data, every time it hits the data, it jumps by 1/n, right? So it will stay at this level. When it hits this point, it jumps by 1/n, and so on until at this point it will go to 1, right? So it's like a ladder. Staircase, right? And there are functions in R. I'm sure all of you know R, right? There are functions in R for computing the empirical. So this is known as the empirical CDF of the data. So the procedure for computing the VAR is this 4-step procedure. So the first is to simulate B. B is the integer. It could be like 100, it could be 1,000 or 10,000, right? Is to simulate B independent random samples, each of size n from f hat, right? And compute VAR by the historical method for each of the B samples. So if you have B equal to 100, you will simulate 100 samples, each of size n. And for each of the 100 samples, you will compute VAR by the historical method. So it will give you 100 different estimates for this. And finally, you take the VAR to be the mean or the median of these 100 estimates. All right, so that's the fun. It's a 3-step procedure, Bootstrap. The next method is known as the Jackknife method. It's also due to Efron, I think. So the procedure is similar, except here, the first step is to compute VAR by the historical method for the data, but excluding the first data point. See what I've done here. So the data is from x2, x3 up to xn. So we have deleted the first data point. The second step is to compute VAR by the historical method for the data, excluding the second data point. So you have x1, x3 up to xn. And the final step is to compute VAR by the historical method, excluding the last data point. So you have x1, x2 up to xn minus 1. So these steps over here will give you n different estimates for VAR, each computed using the historical method. So the final step, the very final step, is to take the mean or the median of the n different estimates for VAR. Okay, so that's known as the Jackknife method. And the fourth method is the kernel method. This is actually a good method. I mean, kernel method is one of the kernel method. Have you done? Do you know what a kernel is? I mean, have you done density estimation? No, in the class, no. All right. Suppose you have the data on losses. The kernel CDF is defined by this, right? Where H is known as the bandwidth, G is given by this, and K is known as the kernel PDF. Usually it's taken to be the PDF of the standard normal distribution. Now H controls how smooth F hat becomes, right? So the larger the values of H, the smoother the F hat will become. So it's like, the kernel estimation is like a more smooth version of the empirical CDF. Remember the empirical CDF I showed you earlier, which is Which is this one, right? This is the empirical CDF I talked about earlier, right? This is not smooth at all. This is like a staircase, right? It's not smooth. Whereas kernel CDF will give you something. It's a more smoother version of the CDF of the data. Okay, and I mean, if you haven't done this, this is so you have, this is the formula for the kernel CDF. Now there are two ways of estimating VAR. One is to take the root of this equation where f hat is the kernel CDF equal to P. And the second method is to use this formula here, where these are the data arranged in increasing order, right? So once again here, f hat denotes the kernel CDF. Okay, so these are two different ways to estimate VAR based on the kernel CDF. All right, so these are the methods, non-parametric methods for estimating value at risk. Any questions, guys, so far? You're keeping quiet today. Oh, one announcement is the Inclass. Some of you guys asked me about the Inclass test. I have decided it's going to be online. So it will be online and it will be held on the 17th of December, which is a Friday. I told you this before, maybe. And the time is the time of the tutorial hours. So it will be from 12 to 1 p.m. So you can do the test from wherever you are. And after 1 hour, you can upload the answers to Blackboard.
So it's like not a so it's like when you write out the step, not multiple choice.
No, not multiple choice. Yeah, it's similar to previous years. There, you should go to the course website. Some of you don't seem to know where it is, so you should go to the course website. I put there the last 7 years Inclass Test and the solutions. Do you know where that is? Yeah. Some of you asked me where, some of you said you couldn't find it. Okay, you should go to the course website, you will see that. So the style of the test will be similar. I mean, this year, the one on 17th of December, it will be similar to previous years. Okay. Yeah, you have 1 hour to do the test. And so when you say we have an hour, yes, that's correct, madam. Yeah, you have 1 hour to do the test, and after that you can upload your scanned answers to Blackboard. Yeah, that's right. Okay, all right, let's go to the next section, which is semiparametric estimation methods for VAR. Well, I think how quickly you can upload it. Maybe you will be given an additional hour. I know some of you guys are still in China, I think. So you may be given an additional hour to upload the answers. Yeah, so you have 1 hour to do the test and 1 more hour to upload the answers. I'm sure in Manchester you don't need 1 hour, but I mean, but if you're elsewhere, somewhere remote or someplace, then you may need 1 hour to upload the answers. I don't know. Okay. Yeah. All right. Okay, the semi-parametric estimation method, which means that the part of the estimation method is parametric, and the other part of the estimation method is non-parametric, right? Okay, so there are two methods I'm going to talk about. The first is the GV method. So suppose the data follow definition 1. When I say data follow definition 1 of extreme values, I mean, you guys remember this picture from a long time ago, right? This is definition 1 of extreme values, where suppose you have, say, 20 years of data, say stock return data, right? So when I say the data follow definition 1, you should take this picture into account. You will have 20 data points. If you have 20 years of data, you have 20 extreme values, yeah? Because you're gonna pick only the largest or the smallest data point in every year. So you have 20 extreme values. So that's what I mean here. That's what I meant when I said the data follow definition 1 of extreme values, right? Then we know from the stuff that we did before, this is the CDF of the data, right? And it follows from this that the VAR is given by this, right? Now, as you can see, there are 3 parameters here, mu, sigma, and psi. Now, there's a popular estimator for psi, which is known as Hill's estimator, given by this. And this estimator is a non-parametric estimator because it doesn't assume anything about the distribution of the data. I mean, it is based only on the data, right? It doesn't say like the data follows a certain distribution or not, right? So this is a non-parametric. Actually, if you look at the Hill's paper, 1975, it says that this estimator is non-parametric, right? Okay, and where's the other one? So that's for this parameter psi. Now, for the 2 remaining parameters, which are mu and sigma, I'm going to take them as the MLEs. So these 2 are parametric estimators because MLE, as you know, assumes that the data comes from a specific distribution, right? So you have 3 parameters of the two of the 3 parameters are estimated parametrically, and one of the 3 parameters is estimated non-parametrically. And hence, this is a semi-parametric estimator for VAR. Right, so that's known as the GEV method. Now, the second of the 2 methods, so let's put it here. The second of the 2 method is known as the GP method. So here, I'm going to suppose that the data follow definition 2 of extreme values. Now, if you remember what definition 2 is, this is definition 2 of extreme values. So here you draw a threshold which is you think is large enough, and any data point that is above the threshold is considered an extreme value. So in this, so here, like you can have more than 1 extreme value per year, right? Okay. All right. So in this case, we know from what we did, the stuff we did earlier, this is the distribution of the extreme value, which is known as the generalized Pareto distribution. And setting this equal to P, you get this as the formula for VAR. Now this, if you look at this formula, it has 2 parameters, sigma and psi. Once again, I'm going to estimate psi using the Hill's estimator, which, as I said before, is a non-parametric estimator. And I'm going to estimate sigma as the MLE. So sigma hat will be a parametric estimator, right? So you have 2 parameters. One of them is estimated parametrically. The other is estimated non-parametrically. So once again, what you have here is a semi-parametric estimator for VAR. Okay. So those are the 2 semi-parametric estimation methods for value at risk. Okay, so these are the 3 videos I asked you guys to watch. And now in the remaining time, let's see, let me show you let me go back to what I showed you earlier, which is I'm going to do, because I realized that some of you might have forgotten this stuff, or maybe this stuff here, right? So I would just do some examples. Right. Let's look at this one here. This is one of the parametric estimation methods I talked about today. And excuse me. Oh man. Suppose these are the losses following the exponential distribution, then the VAR is given by this formula, and the MLE for lambda is this, and hence the estimator for VAR is this, right? Now I showed it can be shown that this is unbiased and consistent. I'm going to show you that now. I'm going to show you that this is unbiased and consistent, right? Right. So I'm assuming that right. Okay. Now, the first thing I like to do is I want to show you that this estimator is unbiased. Now, to show that something is unbiased, you should look back on the stuff I showed you here. What is it here? Now, to show that something is unbiased, you need to show that the bias, which is defined by this, is equal to 0. Yeah. Okay. You see what I've done, what I'm doing. So it's the expected value of the estimator, which is this one, minus the parameter, minus the thing that you're trying to estimate, which is this one, right? So this is gonna be okay. Please let me know if you don't follow what I'm doing. I'll try to explain better. Okay. Are you following me? Let me know if you're not. Now, taking the expectation inside,
Why is it not capital X inside?
yeah, it doesn't matter. Well, it's abuse of notation, yeah, I know. But yeah, it's okay whether you use small x or capital X. Yeah, yeah, it's okay. I mean, and yeah, you're right, Robert. I mean, it should be capital X, but I am just for laziness, I'm writing small x, right? Okay. So this will be now you may remember from your first year that the expected value of an exponential random variable is 1 over lambda, right? So this guy here is 1 over lambda. Okay. So this is the sum of a constant, which is n times the constant. Right, and this is clearly 0, right? So what we have shown that the estimator for var is unbiased. Okay. You guys okay? Any questions, guys, on the Zoom? Are you okay? I mean, some of you might have forgotten this stuff from, I mean, you must have done this in your year 1 or year 2. Maybe you forgot. I mean, it's important that you do refresh your memory because it's gonna come in the exam. So please, if you forgot, please refresh your memory. Okay, so that now the second part of the question is I want to also show that the MSC stands for mean squared error. The mean squared error is approaches 0 as n approaches infinity. So the MSC of var is gonna be MSC of minus x bar times log of 1 minus p. Oh, sorry. Okay. Now, you may remember this from your last 2 years that if an estimator is unbiased, then the MSC is the same as the variance. Yeah. I know here it's going to be confusing because I'm using var for, but maybe I should. Variance is different from var, although they look similar. This is variance. This is not to be confused with var. This, all right. So it's easy to confuse these two. So VAR has a capital R, whereas variance has a small r. So don't confuse the two. Okay. Now, if you take, because this is a constant, you can take it outside. Okay. Because remember, when you take a constant outside of the variance, you need to square it, right? So that's what I have done here. So this is variance of 1 over n taking the variance inside, you get 1 over n squared times the sum of the variance of xi. Now, once again, the variance of an exponential random variable, if you remember, it is, you should remember what that is. Is this 1 over lambda squared, right? Okay. So this becomes this is a constant. 1 over lambda squared is a constant with respect to I. So this is n divided by lambda squared. Okay, so you have okay. So this is the answer. This is the formula for the MSC of the estimator. Now, as n approaches infinity, p being a constant and lambda squared is a constant, so this clearly approaches 0 as n goes to infinity. So hence, the estimator for VAR is consistent. Okay, guys. Are you any questions on this, guys? The Zoom or here? I'm gonna do, if I have time, I will do one example. I may not have the whole time. I'll have some. This example 2. Suppose you have IID normal, and in this case, we know from what we did earlier today that the estimate for VAR is All right. This is the formula for that I gave you, where this is mu hat is x bar, right, and sigma hat is okay. Now this estimator is asymptotically unbiased, which means that the bias approaches zero as n goes to infinity, and consistent, which means that the limit of the MSE is zero. Now, in order to show that is it's not difficult, but the calculations will be pretty lengthy. But I mean, I will. I don't know if you know this, but do you know this result that if you have and this is stuff we did. I think I did this in the first year, if I remember correctly. That is this is distributed as oh, sorry, excuse me, not n minus 1. Sigma squared. Yeah, and also the result that x bar has a normal distribution with parameters do you guys know this? I mean, this is stuff that I talked about in the first year intro to stats course, but you might have also covered this in statistical methods, if you have taken this. These are two well-known results, that this guy here is distributed as this symbol here means sigma squared times a chi-squared variable. This is the notation for chi-squared variable with n minus 1 degree of freedom, and x bar is distributed as normal with these parameters, right? So to find the bias, of this, which is the expected value of var hat minus var. Okay, so this is gonna be the expected value of x bar plus okay, minus so there's no hat here. No one keep meeting. There's no hat. Excuse me. It's just mu plus sigma times phi inverse of p, right? Okay, now you should take the expectation inside. This is gonna be the expectation of x bar plus here is going to be the expectation of this 1 over n, or 1 over square root of n, times the expectation of like this. Okay, are you guys with me or what? I know I'm running out of time. So the expectation of x bar from this fact is equal to excuse me, I need to finish quickly. Expectation of x bar from this fact is mu, and the expectation of this guy here from this fact, it can be shown to be equal to, after a lot of calculations, which I'm not going to go through now, it can be shown to be equal to this. Right? And then you have this guy here. Then you have minus mu minus sigma phi inverse of phi. All right, now I would like you to show what I don't expect. If you can't show, it's okay. This clearly this is not equal to 0. Clearly this, but if you can, I would like you to show that this approaches 0 as n goes to infinity. And hence the estimator is asymptotically unbiased, right? If you can, I know it doesn't look pleasant, but doesn't look pleasant. I mean, the fact that this is equal to this follows from this, and the fact that this is equal to this follows from this guy after some calculations. Okay, I'm sorry, I've run out of time here, but right. But I mean, if you can't show this, it's okay. If you can't show that, don't worry. But if you can show that this approaches, sorry, this whole thing approaches 0, that's great. All right, guys, so I will see you on Friday. I'll try to, I will email your mark and feedback later today.